So far in Unit C, we've solved systems through graphing and realized there's three different options when we are solving systems of equations. So we could have a unique solution, a consistent system, an x and a y that makes both happy. We could have a dependent system where the lines might look different, but they actually make the same line, and that would have an infinite number of solutions. Or we could have an inconsistent system where the lines actually ran parallel, they had the same slope, and that's the case where there's no value of x or y that's ever going to satisfy both of those equations at the same time. They're never going to touch each other. So hopefully we have a good start on this with solving by graphing. We're going to move into C2 and C3 in an algebraic approach to these. And so we're going to still be dealing with these systems of equations, but we're going to have a different strategy to figure out what the solution to these systems are. And so the first process that we're going to learn in C2 is solving through substitution. Basically, what we're going to do is take the two equations and substitute one into the others. In order to do that, we have to have one of the equations solve for just one of the variables. So you'll see in this first example, this second equation is solved for y. And so what we're going to do with that is take that and sub into our first equation. So every time I see a y, I'm going to sub in this 3x. So if I rewrite that, I'd have x plus 3x, because that's what y is equal to, equals 12. So in doing this, what I've done is I've eliminated one of the variables, right? If I collect my like terms right now, I have 1x and 3x. So I get 4x equaling 12. I can keep going and solve for x. That's going to tell me that x equals 3. That is only half of the solution. Remembering I have to have an x and a y. So in this one, what I'm going to do next is take that x value and sub that into equation 2. So my equation 2 says y equals 3x. Well, what I'm going to do is replace the x with this 3. So I get that y equals 9. And the whole name of the game for this is that this is a consistent system. I have found the x and the y values where these two lines would intersect. I have 3 and 9 as the solution to this consistent system, right? What I could do with these ones, if I really wanted to, I could take and I could verify. Equation 1, left side and right side, these x's and y's should make that true. Equation 2, left side and right side. If I sub x and y in, so 3 and 9 in, it should make it true. So without drawing the pictures of these, I found the point where these two lines intersect for this consistent system. And really the strategy in this is this substitution bit. So let's take a look at these. When I do these, I always label my equations because that helps me keep things straight. I also do these funny arrows with my instructions of like, well, what am I doing here? So what I'm going to do with equation 1 and 2 in this second system is take equation 2 and sub it into equation 1. Remember, we sub in with brackets, and what we're really doing here is where I see a y in this first equation, I'm going to replace it with this big thing. So what that's going to look like, I'll give myself a little bit of room. I'm copying equation 1, so 2x plus 3 times y. So y is actually equal to the 2x minus 7, right? That's substituting this whole thing in for that y. And keep copying, equals 3. So what I need to do now with this thing that I've made here is solve for x. This has some distributive property going on. That's why it's important to sub in with the brackets. I'd have plus 6x and minus 21 equaling 3. What I'm trying to do is solve for x. So the next thing I'm going to do is collect those like terms. I have 2x and 6x, so that gives me 8x minus 21 equaling 3. And I'm now going to add 21 to both sides. This gives me 8x equaling 24. Finish it up, divide by 8 on both sides, and I get that x equals 3. So what I'm going to do with that, I'm just going to scroll to give myself a little more space here, is I'm going to take that x, because that's only half of my answer. I'm now going to take that and sub it into my equation 2. You could take and sub it back into equation 1, but the reason I pick equation 2 is that it was already solved for y. So there's less for me to do. There's less place that I could make a mistake. And again, what I'm doing here is replacing the x with this value that I've just found. So now I do the math. I get 6 minus 7, or y equals a negative 1. And so finally putting this back together, I could write this solution as an ordered pair. And that's the point where these two lines intersect. If I take this is my x and this is my y, I could, if I wanted to, and I don't have the space on the page and I'm not feeling that inclined to do this, I could take and I could verify the first equation and the second equation with those values, because those are the values that make both of these equations true. All right, so a few more of these. We'll get the hang of it, hopefully. I start by numbering my equations, and then I do this funky bit of writing my instructions out on the page. Even if I'm not doing it for someone else, I kind of do this process. So I am choosing to take equation 2 and sub it into equation 1. Specifically, I know in equation 2 that y equals 4x. So that's what I'm going to replace the y with in that first equation. So I'm working with this first equation. So x minus, subbing in with brackets, 12. So now I have x minus 4x, so minus 3x. They're like terms, so I can actually do that, equals 12. Solving for x, I get that x equals a negative 4. And if you remember from the top two, I'm only halfway done. I'm going to take this x value and sub it into equation 2. So what that then looks like is y equals 4 times negative 4. Y equals a 16. And you can imagine this would be hard to put on a graph unless I gave you, oh, negative 16. Forgot the negative sign. So this would be hard to put on a graph because negative 16 is a long way down there. So what we've done is found the point where these two lines intersect. We found the x and the y that satisfies both these equations at the same time. More of these, more negatives, more complicated values. Same approach. I've got my two equations. My second equation in this time is solved for x. I don't care if I solve for y's first or x's first. It doesn't really matter. But the thing is, I have to have some statement that represents one of my variables. So in this one, what I'm doing in equation 1 is replacing the x with this 4y minus 2. So in a sense, I'm subbing into equation 1. So starting with equation 1, I've got a 2 and I've got an x. So that would be 4y minus 2 minus 3y equaling 6. Just copying the rest of it. I've got this funky distribution or distributive property. So 8y, and don't forget to do the second one, negative 4. I'm just going to copy out the rest. And then in this one, what I'm solving for is y. Again, it doesn't matter which variable you solve for first. I'd have 8y minus 3y, so that's 5y. I'm not going to do anything with the other stuff. I'm just going to copy it down. I would add 4 to both sides. I'd have 5y equaling 10. And solving for y, dividing by 5 on both sides, I get y equaling 2. So all good. I'm halfway there. I'm now going to take this value and I'm going to sub it into equation 2. That would give me that x equals 4 times 2 minus 2. I've replaced the y with a 2, like my instructions tell me to. So x would equal 8 minus 2, or x would equal 6. And putting this back together, this would be a consistent system. Kind of drop that word. But we've got a point where the two lines would intersect. I have an x and a y value that would make both of those equations true. Top of the next page, we have some more. And just as a reminder, there are the answer keys on the Moodle site that you could always go to. If you don't need all of the examples, you can always use those as well. Or heck, you can fast forward me or whatever you like to do. So in these ones, we have something that's a little different. So I have two equations. I'm going to start with 1 and equation 2. And in these ones, I don't have one of them that is solved for one of the variables. So I'm going to look at them closely and I'm going to make a decision which one I think is easier. I'm going to play with equation 1 here to solve it for x. I could do that by adding 2y to both sides, right? So maybe what I might do is fix that up before I call it equation 1. So what I'm doing with this one is saying now that x equals, 2y plus 5. Now I have something that's a little bit easier. So I could take equation 1 this time and sub that into equation 2. What I'm going to do then is say 3 bracket 2y plus 5 plus y equals 8. These ones, it takes a little concentration. Sometimes I copy things wrong. Hopefully I won't in my making the videos here, but just kind of following the plot, right? It's complicated. And what we're doing is taking all of this and replacing the x value. So if highlighting your work like that helps, go ahead and do it, right? Okay, so I have some distributive property to do. 3 times 2y gives me a 6y. 3 times 5 gives me a positive 15. I'm just going to copy the rest of it. Things are working out, so I only have one variable, and I can solve for this. I'd have 6y and 1y, so that's 7y. You can do more than one step, but I tend to make mistakes, so I don't. Still solving for y, I get down to this point that 7y equals negative 7. Watch your signs, use your calculator, try not to make silly mistakes. This tells me then y equals a negative 1. I can take that and sub it into equation 1. As long as I didn't make a mistake in reordering this, x is now going to equal 2 times negative 1 plus 5, right? This was equation 1 that I had made, and so now I'm solving for x. X would equal negative 2 plus 5, or x would equal 3. And that's an ordered pair, so I've got a 3 for my x and a negative 1 for my y. With just the powers of algebra, not drawing these on the graph, I found the point where these two lines would intersect. I found the x and the y that satisfies both of these equations at the same time, that makes both of these equations true. If you want, you can challenge yourself to this one if you want to give it a try. You may find that there's a different route to these. So you might end up with the correct answer, but your work might look different. It's kind of a choose your own adventure. You can make choices of how you treat these and then the order you sub things in. So if you do have answers that are different than mine, answers that are different are not okay, but process that's a little different. If you get to the right place, it's all good. So with this one, I can see that neither one is solved for x or y. I'm going to take this second equation and reorder it so that it now says x equals a negative 4y plus 6. That's what I'm going to call equation 2 here. And I'm going to take that and sub it into equation 1. So copying equation 1 out, now replacing the x with this big ugly thing down here, and copying the rest of equation 1, I can now solve for my y value. I've got distributive property. Copy the rest. I'd have negative 13y. Numbers are a little ugly in this one. I'd subtract 18 from both sides. Remember, you add and subtract everything first before you divide. So negative 13y equals, oh, look at that, negative 13. Things are coming together. I'd end up with y equaling a 1. Negative 13 divided by negative 13 is 1. And what I can do with this now is take that back to equation 2. So I'm going to sub this now into equation 2. So x equals a negative 4 times 1 plus 6. X would equal negative 4 plus 6, or x would equal 2. And so what I can do with this at the end is give it as an ordered pair. This is a consistent system. That's the point where the two lines intersect. So far, these have only been consistent systems. We need to now take a look at the other two options for systems of equations. So what does a dependent system look like when we solve it? What does an inconsistent system look like when we solve it with algebra using the substitution method? So in these ones, one of these is going to be dependent and one is going to be inconsistent. We're going to walk through them in the exact same way, and then we can add some notes about what the reality is. What do we see when we're using this strategy? So for A, I'm taking equation 2 and subbing it into equation 1. So where I see the y, I'm writing 2x minus 3. And then I'm going to solve for x. I'm distributing. Watch your negative signs. So 4x minus 4x plus 6 equaling 6. Things are getting weird here. Where 4x minus 4x is 0, I'd have 6 equaling 6. You could keep going, subtracting 6 from both sides and getting down to 0. Once you get to a line of truth, so example, 6 equals 6, 0 equals 0, whatever it is, when one thing equals another, it could even be 4x plus 2 equals 4x plus 2, right? Once you get down to something that's absolutely true, that tells you that this system is a dependent system. It tells you could pick an infinite number of xy terms or xy coordinates that would satisfy both of these at the same time. They're actually the same line, even though they look very, very different up here. So there's an infinite number of solutions. And really the key thing here is how you recognize it when you're using algebra. You're not drawing pictures, and we're looking for this line of truth. Okay, so let's walk into the other one in a similar approach. I'm going to say equation 1 and equation 2. Equation 2 is already solved for x, so I'm going to take and sub that one in there, replacing the x with this 2y plus 2. Using distributive property, I'd get 6y plus 6 minus 6y equaling 9. At this point, if you collect your like terms, you have 6y minus 6y, so that goes away. And what you'd be left with is 6 equaling 9. You're left with a line of garbage. I call it garbage or nonsense. So 3 equals 2, 0 equals 3, any of this, 6 equals 9, that is my indicator that this is an inconsistent system. There are no solutions for this one. It's absolutely impossible to satisfy these. These would be parallel lines. You can't see them in this format, but that's what we did in the solving by graphing. So now, as we're using powers of algebra and this addition, this substitution approach, this is what you're looking for those two other options. So we've got 4 more to do on the other page, and these are kind of a mixed bag. They may be a consistent system, they may be a dependent system, or they may be an inconsistent system. To be honest, I kind of am relieved when I get down to a line of truth or a line of garbage, because it's basically half the amount of work as a consistent system. The consistent systems feel great because you've got solve for x, solve for y, you get a nice neat answer. But honestly, you're going to take half the amount of time when it's a dependent or an inconsistent system. So let's walk into the next page with this same approach that we've been doing. You shouldn't have to be able to see when it's going to be one or the other, right? So in this system of equations for D, I can see that my second equation is solved for Y. So that's going to have me sub that into equation 1. So where I see a Y up top, I'm going to replace it with this 3x minus 2. Distributive property gives me my next line of 12x minus 12x plus 8 equaling 8. I now have 8 equaling 8 because that 12x minus 12x is 0. That is a line of truth. That tells me I've got an infinite number of solutions, or it's a dependent system. See, half as much work. All right, let's try this next one here. So we've got equation 1 and equation 2. I can see that the second equation is solved for y, so I can take this and sub it in for the y up top. So when I do that, I'm going to start up high, give myself enough space. 4x plus 5, and y is what we're saying is equal to 2x minus 10. Remember in the last section when we were evaluating a function at something other than a number? That's why we did this back in Unit B, because that's the skill that we're now using. So we're now going to hopefully take this as far as we can. I'd have 6x minus 10 equaling 6. I think oh, look at what I did. I did not actually multiply the 5 times the 10. That is a classic mistake I do. Even when I draw those arrows, that's something that I do. So 5 times negative 10 is negative 50. There we go. I'm going to add 50 to both sides. Oh, and look at that. Okay, 4 and 10 is not 6. My goodness, sorry about that. Making so many mistakes over here. Okay, I'm adding 50 to both sides like I said I was going to. I get 14x equaling 56. I'm dividing by 14. Use your calculator if you need. X would equal 4. This is my indicator. This is going to be a consistent system. This is the one that I'm only halfway done on. So once I get an answer, even if it's x equals 0, whatever, I can now find the other half of my answer. So I'm going to go back to equation 2 with this. So y would equal 2 times 4, right? I'm replacing the x with the 4. So y would equal 8 minus 10, or y would equal negative 2. And so what this tells me is that I've got a mistake in my answer key. I will fix that up for us. We've got 4 and negative 2 as a solution to this system. All right, hopefully I won't make as many mistakes on the last 3 here. I'm going to do G just because it's kind of hanging out here next. I've got my 2 equations. I'm going to substitute in the 2x minus 4 for the y. I'm going to do distributive property correctly in this line, hopefully. Negative 8x and plus 16 equaling 16. I'm going to, get down to a line of truth. If I'd subtracted 16 from both sides, I would get down to a different line of truth. It doesn't matter what this is. If one thing equals another, that's your line of truth. That tells you your system is dependent. And really, there's an infinite number of solutions. And as a reminder, what we were talking about is these are actually the same line on the graph, even though they look different. All right, so the last 2 to round out this approach here. We've got equation 1 and equation 2. I'm going to take 2 and sub it into 1. So rewriting equation 1, I'm going to replace the x with this negative 3y plus 1. I'm going to copy out the rest of equation 1 and do my distributive property. I get down to a line of garbage. I get down to a line of nonsense. That tells me that this is an inconsistent system. Tells me it's going to be difficult because it's actually, there's no solution to this. We can't see it from the equations, but if we were to put these on the graph, they're actually going to run parallel to each other. They actually share the same slope. And that's why they would never intersect. There'd never be a value of x and y that makes both of them happy at the same time. H gives us one last try at kind of this choose your own adventure. I have two equations there, but neither one of them is solved for one of the variables. I'm going to pick on equation 2 here. So that's going to be my equation 1. In equation 2, I'm going to take a couple steps. I'm going to solve it for x. And so I'd get that x equals negative 1, sorry, positive. I'm trying to do too many steps at one time. I'm going to slow it down because this is the way you're going to be doing it. So let's just do this in a couple steps. I'm going to minus 3y on both sides. So I get negative x equaling negative 3y minus 1. Divide by negative 1, divide by negative 1. I get x equals 3y plus 1. There we go. That's what I'm going to call equation 2. That's what I'm going to sub into equation 1. That was more work than I could do in my head, as was evident by my stumble there. And so now I'm going to start that first equation, subbing this 3y plus 1 in for x. Doing my distributive property. I'm super nervous, I'm going to do it wrong again. I'd end up with 4 equaling 5. 4 doesn't equal 5. That's a line of garbage. That tells me that this is an inconsistent system. Tells me that it's going to be impossible to satisfy this. There is no solution to this system of equations. They may look super different. If I were to put them in mx plus b form or put them on the graph, I can see that they shared a slope. And so that is really why they would never intersect and there would be no solution. The next section of notes is going to give us another algebraic approach to solving these, and we're going to stay with these three options of consistent, dependent, and inconsistent.